Welcome to Tech Orbit. Enjoy this super video and don't forget to subscribe so you don't miss the next ones.
Is orbiting at a speed of just 24 kilometers per s, so we are moving significantly faster than our target planet, which means that we are going to overshoot the planet Mars and end up stuck somewhere in the asteroid belt unless we start slowing down. After several months of coasting through the vacuum of space, we need to execute our first deceleration burn after flipping the Starship around and getting the Raptor engines back up to speed. We have to shave off 0 velocity in order to become captured in the gravity well of Mars. This is the first step in what's about to become a very rough ride if we burn off another 0, height of the outer moon Deimos 0. A further delta V gets us down to the inner moon Phobos. Here's where things get really tricky. By slowing down this much, we've already expended over 5 kilometers per s of the potential delta V in our fuel tanks, and that leaves us with somewhere between 1 and 2 remaining, but we need at least another 4.5 km/second of delta foive to safely reach the surface in theory. This is still possible as long as we are very strategic about how we use our last bit of fuel. And it's important to remember that everything from here on out is purely speculative. This is our interpretation of the most logistically feasible Mars landing if we want to conserve as much fuel as possible for our landing burn. Then we need to take advantage of some external forces to slow our ship down to a reasonable velocity. Getting down into a circular low Mars orbit would use up most of our remaining fuel, so we probably shouldn't do that. In this case, we might be better served by inserting the ship into an elliptical orbit, so instead of flying in a circle, we're moving in an oval pattern with a low spot, or peri, close to the planet, and a high spot, or api, deeper out into space. By using this maneuver, we can start to take advantage of both aerodynamic drag and Mars gravity to help us slow down. The Mars atmosphere is still very thin, but we'll take any help that we can get. We can lower the pair of our orbit down to the point where the ship actually dips into the upper atmosphere of the planet. By doing this very carefully, we can actually catch some atmospheric drag and lose a small amount of velocity before getting flung back out to our apogee, where, if we've done this properly, the gravity of Mars will pull us back in to repeat the process over again. Every time that we dip into the atmosphere, we gain a little more of that precious delta V, bringing us closer to the velocity we need for a soft touchdown on the planet's surface. But we can't keep this maneuver up indefinitely. Eventually, we need to transition from a shallow dip to a full-on dive through the Martian atmosphere. It's actually pretty difficult to achieve a landing trajectory for Mars because the planet is only around half the size of the Earth. That means the angle of attack necessary to get down below the sky is pretty steep. This means you need a lot of energy pushing the vehicle down in order to prevent it from skipping off and shooting back up into space again. We want to save our engines until the last possible moment, so that force to push the ship down deeper into the atmosphere needs to come from somewhere else. This is why the original SpaceX design for an interplanetary transport system in 2016 had an aerodynamic lifting body in the upper stage. Starship is much smaller than its, so it doesn't need as much aerodynamic force, but the methodology is still pretty much the same on its final approach. Starship is actually going to flip over and come into the atmosphere upside down, so that's with the belly and tail pointed up and the nose pointed down. This way, the lift generated by the body is going to push the vehicle towards the surface on a steeper angle. To achieve entry, we're also going to start losing a lot of velocity thanks to aerodynamic drag. Once the angle of attack is set, the Starship is going to flip around into the more traditional belly flop maneuver that we've seen on Earth. This is all about creating the maximum amount of drag that is physically possible and getting the velocity down. But this force can only accomplish so much. The maximum speed of a free fall is something that we call terminal velocity. Imagine you jump into a bottomless hole. Your body will accelerate as you fall up until a certain point when the drag and buoyancy of your body equalizes with the force of gravity and your speed becomes constant. One way that we cheat terminal velocity is by using a parachute. This greatly increases drag and slows down our terminal velocity. Starship isn't going to use parachutes, so there's going to come a point where the aerodynamic drag of the vehicle has done all that it's going to do, and we reach terminal velocity due to the thinner atmosphere. terminal velocity on Mars is around 5 times faster than on Earth. In other words, that means you only get 1/5 the delta V accomplished by Belly, flopping through the air on Mars compared to what we've already seen Starship do on Earth. Which means that it's going to require more engine power to land on Mars than it does on Earth. This is why fuel is such a major concern here. Assuming that everything up until this point has gone correctly, the Starship's engines will fire up one last time and flip the tail towards the surface, at which point the fuel in the rocket's header tanks will provide just enough delta Phi to bring our ship perfectly in sync with the surface of Mars, and we touch down softly. Now that's a lot of stuff that has to go. Right, and there is zero margin for error. You either score 100% on the exam, or you die, so by knowing all of that we can appreciate that landing on Mars is going to be incredibly difficult in a massive vehicle like the Starship. It's much easier for NASA to land smaller and lighter vehicles on Mars because the potential delta Phi of your fuel is determined by the mass of the vehicle and the efficiency of the engine. So 1 pound of fuel accomplishes more change in velocity for a lighter ship than it does for a heavier ship. And there is a limit on the amount of fuel that we can bring to Mars. Starship would be much easier to land on Mars if it were lighter, but SpaceX needs it to be so gigantic to accomplish the goal that Elon Musk has set out, which is building a self-sustaining city of 1 million people on Mars. SpaceX is working hard on increasing the delta V of the Starship. They want to make Starship V2 longer with bigger fuel tanks, while also making it lighter at the same time and adding 3 more Raptor vacuum engines. The third version of the Raptor is currently in design and will probably offer higher efficiency and therefore more delta V potential. Now there are other more long-term solutions as well. Remember Mars's outer moon Deimos, the delta V required to move from low Earth orbit to the orbit of Deimos is only around 5/2. That's a lot more manageable. And imagine if you could build an outpost or a Mars gateway at the orbit of Deimos. Now we have the potential to refuel the ship so that it can make the hardest part of the journey with more. Then enough delta Phi to spare this buys you a margin of error that would increase the safety of a Mars landing by orders of magnitude. So yes, landing a fully loaded Starship on Mars is going to be logistically insane. This is one of those situations where SpaceX won't know anything for certain until they try. We've seen this twice now with just launching the Starship, and both times it exploded in mid-air. Learning to land on Mars is more than likely going to be a similar affair. They are much more likely to fail before they succeed. They could fail multiple times. It's going to require a spectacular amount of willpower to make this work, to not give up, and probably more than a lot of people are genuinely prepared for. And then eventually we try to do this with people on board, and calling this ambitious seems like an incredible understatement. But over the history of humanity, we've accomplished the impossible many times over. So what's one more? Meet us back here every week for more updates on everything aerospace industry and interstellar exploration related. Make sure to give the video a thumbs up today if you liked it. That really helps us out for real. And subscribe to the Space Race for more videos. Just like this, we do 1 long form essay and 1 news update every week. And if you'd like more, we've got 2 more on the screen for you right now.
That's it for today's video. Don't forget to subscribe, like, comment and activate the notification bell so you don't miss any videos. See you soon.